everyone, my name is Ariy'Ana Duke, and today I'll be presenting my group's project on optimizing altitude of low orbit satellites based on Starlink satellites. To begin, what is Starlink? Starlink is a constellation of small satellites developed by SpaceX, and it's the world's largest network of low Earth orbit satellites, designed to provide high-speed internet access to even the most remote and underserved areas. However, the system relies heavily on precise orbital maintenance to deliver uninterrupted service. This research is significant because low Earth orbit satellites like Starlink are key to global connectivity, and understanding how solar activity affects them can help ensure their sustainability and reliability. And that's where the challenge arises: solar activity. Solar storms and increased solar winds can disrupt these satellites significantly. Today we'll dive deeper into this challenge and how we address it. A recent event highlights this problem. In February 2022, 40 Starlink satellites were deorbited after a major solar storm. During the storm, a geomagnetic disturbance increased atmospheric density, creating higher drag on the satellites and causing them to lose altitude. This event shows the vulnerability of low Earth orbit satellites to solar activity. It also shows why accurate models to predict and mitigate these effects are so important for maintaining satellite constellations like Starlink. We should explore the science behind these effects. So the sun emits a constant flow of charged particles known as the solar wind, made up of high-energy electrons and protons. During periods of increased solar activity, this wind intensifies, causing geomagnetic storms. These storms can interfere with satellite control systems by affecting magnetic field sensors, accumulate charge on satellite surfaces, and leading to discharges and potential damages. Lastly, they can interact with propulsion systems like Starlink's krypton-ion thrusters, reducing their efficiencies. Also, atmospheric drag is a temporary increase in solar activity that can cause change in atmospheric density. Another key concept here is the F10.7 index, a measure of solar activity. Higher F10.7 values indicate stronger solar activity, which has a greater impact on satellites. The impact of solar activity on Starlink satellites are profound. First, atmospheric drag increases as solar activity intensifies. The solar wind boosts electron density in the atmosphere, increasing drag on satellites, causing them to lose altitude. Without corrective action, satellites risk deorbiting as seen with Starlink satellites in the 2022 solar storm. Secondly, geomagnetic storms interfere with onboard control systems, making it harder to maintain their orientation. Finally, surface charging from high-energy particles can damage critical electronics, where discharges can damage or cause system malfunctions. This combination of challenges shows the need of careful modeling and optimization of satellite behavior in response to solar activity. The main goal of our project is to calculate the optimal altitude for a given solar activity index value and visualize the satellite's trajectory using animations and graphs to better understand its motion and behavior. We use the Runge-Kutta fourth-order method to simulate the satellite's motion in orbit. We use this method because this is widely used in numerical simulations because it is reliable for solving differential equations. We use path loss as a key component of the cost function along with thrust energy to determine the optimal altitude for maintaining orbit and communication efficiency. These methods together allow us to model satellite behavior in low Earth orbit. This is how we calculated the optimal altitude for a satellite. The goal is to minimize the combined effects of thrust energy consumption and communication path loss. The cost function we use is defined as this function right here, where E thrust is thrust energy consumption at altitude h, where LPH is the path loss at altitude h. We use this MATLAB function, fmin_bnd function, to minimize this cost function and calculate the optimal altitude where the optimization is performed between hmin 300 kilometers and hmax being 1200 kilometers. The calculate optimal altitude function is shown here. The whole MATLAB code is shown here, where this function dynamically adjusts the altitude to minimize the combined cost. Here, this explains how we calculated the satellite's orbit by integrating its orbital dynamics using the fourth-order Runge-Kutta method. The goal is to calculate the satellite's position and velocity as it orbits Earth. These equations describe the satellite's motion. The first formula is the rate of change of position equaling velocity. The second formula here is the rate of change of velocity depending on gravitational acceleration and drag forces. We use the RK4 orbit function right here to numerically integrate these equations. The function breaks down the orbit into small time steps and calculates the satellite's position and velocity at each step using intermediate estimates. Here, these k values represent different approximations of the changes in position and velocity over the time step. And here we have the code for this process at the top. This function allows us to predict the satellite's orbit step by step. While over here we have the orbit's dynamic function, which allows us to predict, where the gravitational force is pulling the satellite toward Earth, and the drag force depends on atmospheric density, the drag coefficient, and the satellite's velocity. These forces combined allow us to compute the total acceleration acting on the satellite at each step. And here's the corresponding code. This method allows us to simulate the satellite's motion accurately, accounting for gravitational forces and drag effects due to their solar activity. Here, we calculated the thrust energy required to maintain the satellite's orbit and atmospheric density, both of which are key components in understanding orbital dynamics. The thrust energy represents the energy consumed by the satellite to overcome atmospheric drag and maintain its orbit. The formula is shown here, where F drag is the drag force acting on the satellite, V here is the orbital velocity, and T is the orbital period. We use this drag force formula with the constraints based on the Starlink satellites, which is shown here. Here's the MATLAB code we use to calculate the thrust energy. This function combines all the components to calculate how much energy the satellite needs to counteract drag over one orbital period. The atmospheric density varies with altitude and solar activity, shown here. We use the following formula, this one, which accounts for both altitude and the F10 solar activity index to calculate atmospheric density, along with the whole MATLAB code. We produce results that show how the thrust energy versus altitude looks like, which is the graph on the left right here, which shows how energy consumption decreases as altitude increases due to reduced drag. In the right here, this is the path loss versus altitude graph, which highlights how communication performance worsens at higher altitudes. Lastly, we were able to show the cost function versus altitude, which is this graph on the right, combining these factors, which shows the optimal altitude where the cost is minimized, marked by the red dots. This balance is crucial as it shows how Starlink satellites periodically adjust their altitude to maintain optimal performance and avoid excessive energy consumption. Now we can take a look at our simulation that my group created to visualize how solar activity affects satellite altitude. On the left over here is a 3D visualization of a satellite's orbit around Earth. This is a simplified Starlink-like trajectory in low Earth orbit. As the satellite moves along its path, its altitude gradually decreases over time due to atmospheric drag. This drag is influenced by solar activity, which increases the intensity of the upper atmosphere, particularly during geomagnetic storms. Overall, this depicts nonlinear altitude loss, which it fluctuates due to variations in atmospheric conditions, orbital velocity, and drag forces. The importance of the simulation is that it demonstrates the dynamic behavior of low Earth orbit satellites under different solar activity. As we can see on the two graphs over here, where the first one shows the F10.7 index being 75, while the F10.7 index being 200. Looking forward, there are several areas for improvement. We can conduct longer simulations to study the cumulative effects of solar activity over months or even years. We can incorporate real-world communication data to refine path loss models and improve signal reliability. We can also simulate performance under extreme solar conditions to better prepare for rare but catastrophic events. To conclude, we've shown how solar activity affects low-orbit satellites like Starlink and demonstrated a model to optimize their altitude. Our significant findings include how higher solar activities require satellites to operate at higher altitudes to reduce drag, and that satellite sustainability depends on frequent altitude corrections and reliable modeling. By developing accurate models and adaptive control systems, we can assure the long-term success of satellite constellations, maintaining global connectivity, and reducing the risk of satellites deorbiting. Thank you for your attention, and please feel free to leave any questions in the comment section. Thank you.